let's start. And okay, welcome to the second part of our course of lectures. Please.
Okay, so good afternoon, everyone. Thank you for coming back. So now, today we are going to talk a little bit based on everything we discussed yesterday. I just want to give you a glimpse of the possibilities that are out there, because there are a lot of other possibilities beyond the normal methods that we talked before, and I also want to talk to you about a few applications to astronomy. So again, if you have any questions, just interrupt me in the middle of the talk. That's not a problem. So just a summary of what we're going to talk about today. So I'm going to first do some updates on some things that I said yesterday. I'm going to talk about other types of learning. I'm going to do a brief introduction on neural nets and deep learning, and I already let you know that I am not a specialist at all in deep learning. So I'm going to go very briefly through it, and then I will spend most part of my time actually talking about adaptive learning, which is the field that I am most active on. So after my talk yesterday, I realized that one, there were a few questions that I said I would answer and I did not answer in my talk, and also there are a few questions that people came and talked to me after the talk that I would like to clarify, some things that were not clarified. So one of the questions that were asked was, in unsupervised learning, how do I decide the number of groups? Because I talked about k-means, and in k-means you have to give the number of groups as an input, right? You remember that. And the question always arises, well, if I don't know the number of groups, how do I choose? There are many different methods and many different metrics that you can use in order to decide the number of groups, but in one way or the other, they all going to be based on of some metric that minimizes the intra-cluster distance. So you want the members of your cluster to be very tied up together and maximizing the extra-cluster distance. So you want different clusters to be as far away as possible from each other, because then you would have very clumpy clusters far away from each other that would categorize your cluster. So even if you have an unsupervised learning model, for example, last time I talked about self-organizing maps, that actually doesn't give you groups, but it gives you distances between objects from which you can define these kind of things. And also, even if you take some density-based unsupervised learning as dbScan or something like that, there are always going to be some metric that tries to minimize this and maximize that. And this is more or less how you try different number of clusters, and you choose the number of clusters which maximize this distance and minimize the intra-cluster distance. Okay. And the other thing that was pointed out to me was that I said that I didn't know about what was happening in Bayesian machine learning. Someone pointed out that you can use your likelihood as a loss function, and then you would kind of have an interpretation for what you're doing. But I went to check, and actually there's a whole bunch of people working on Bayesian deep learning. So this is an IMS workshop that happened last year. But if you look at the people, I'm not sure if you can read, but if you look at the people that are the speakers, they are basically people from industry, from Google, DeepMind, and things like that. So there is a lot going on like that. I even found a Python library for Bayesian deep learning, but I'm not going to pretend that I understand the principles that are behind this, but I really think this is pretty interesting. And I also look at some academic articles to see if this thing has been done in academia. I found references on biology, on image recognition, in natural language processing, and none in astronomy. Maybe it's my fault, but I couldn't find any applications in astronomy. So this would be a very nice way to do it, I think. Questions? Mm-hmm. Okay. So other types of learning. So last time I talked about supervised and unsupervised learning. You can also have semi-supervised learning. Semi-supervised learning means that remember that in the supervised scenario, you have a training sample for which you have the labels and the features, and the target sample for which you only have the features. In semi-supervised learning, you will use the information that is in the target sample. Even if there are no labels, you have some information there. So for example, if you want to classify, you have only these two label data points, and you want to find the boundary between them, basically anything can do, because you only have 2 points. But if you plot all the points for which you do not have labels, you see they kind of cluster together. This might help you draw a line in between your points. This kind of thing has already been used in astronomy in the case for supernova photometric classification. So the normal pipeline is you have your data set, which is very bad and inhomogeneous and very ugly. You homogenize it somehow, do a dimensionality reduction, and then you put that into some machine learning algorithm. In this step, where you do the dimensionality reduction, instead of using only the training data, you also use the target data in order to do the dimensionality reduction. So this means that you are using the information that is available in the features of your target sample in order to define your parameter system. So you see that this is only the target sample and only the training sample, and all of these things here are the target sample, the target sample, and all of these things here is the training sample. So obviously these are very blurred. You can see that this classifier is not very good, but it actually allow them to be a reasonable good classifier, especially if you have a representative sample. Other possibility is transfer learning. Yeah.
Can I ask a question?
Yeah.
And before the slide before,
This one.
why the dimensionality reduction is done for this case? Is in order to apply semi-supervised learning, or is obvious step what you use in supervised learning too?
Yeah, so the normal supervised learning tool includes a dimensionality reduction step in many times, because you want to
lose information when you apply dimensionality reduction, because
yeah, you lose, but sometimes your data matrix is just too big, and in this case it was not. In this case, they were really trying to do some feature extraction. They were really looking for which one of my features are actually going to be important to whatever I'm doing, because they had, I think, they had a complete matrix, so like 200 columns or things like that.
But feature reports, it's like more about visualization. You want to know and to understand which features are important. But when you use all the bunch of features, the modern methods like random forest or gradient boosting can work very well with all these sample features without need to...
Yeah. So in this case, actually, you were right. In this case, actually, the classifier that they used was a random forest. But as they have in the beginning a very huge matrix to deal with, your random forest needs to be very deep. You go very far away in the random forest. And it's not only feature extraction in the way of understanding which one of your columns is important, it's it's dimensionality reduction in the sense that I'm trying to find a combination of my features that would include the highest possible information, because this data is very bad. So I know that many of the things that I have there, they're basically noise, they're not saying anything. So when you do, for example, you can do a BCA or something else. In this case, they did, I think it was diffusion maps, in order to find a direction in the parameter space, in the high-dimensional parameter space, where your data could be more meaningful, and then you could get array of the noise a little bit, because the data is very,
about
very
the random forest, all the examples what we have in astronomy, like photometric redshifts or star galaxy classification, told us that when you obtain more features, it works better.
Yeah, in the photometric redshift case, yes, I agree, because in the photometric redshift case, you only have a few magnitudes, And actually what you're trying to do there is any information that you get on top of that is beneficial to the problem. That I agree. On this case, I don't believe this is the case, because in this case, there's a lot of pre-processing during before. You can put the light curve in the matrix, and in the end, you know that you have a lot of features that are not telling you anything. You have to try to arrange them in a way that they are more meaningful individually, like the combination of them are more meaningful than the features itself. But I completely agree with you in the case of photometric registers. Okay, so, but the point here of the semi-supervised learning would be, as I said, to use the information that is in your target in order to help define the low-dimensional feature, the low-dimensional feature space. So you are using that information even if you do not have labels in your data. Another option would be transfer learning. So there are two options of transfer learning. Transfer learning is when you take the information from someone else. So you have your data and you do not believe you have enough information in your data set. So you can use information in someone else in order to help you start with, and after that you start training. So one of the options that you can find in the literature a lot is if you do not have enough good data for training, you can, if you trust your simulations, you can do simulations. So you do simulations, you kind of start your analysis from the simulations, and after a while you put that in your data and you use that as a kickstart for your analysis. Another possibility is, suppose that you want to study spectra of a type of star, for example, I don't know, any kind of star, and you do not have enough data. But you do have a lot of spectra from many other sources, right? So what is possible to do is, if you use all of the spectra of other objects in order to reduce the dimensionality of your parameter space, what you're actually doing is you are teaching your model how to recognize what a spectra is, even if it's not the spectra of the given star that you want to study. So if you put a huge matrix of spectra, the code will understand that deeps are important, that widths of features are important. And in this way, you will have something like this. So in this case, it's the principal components. I had no reason. I took a huge matrix and I did principal component analysis on this. These are the first and fifth components. I had no particular reason to choose these two just because they kind of form a heart and I thought it was beautiful. But I just wanted to understand that all of the gray crosses here are spectra from many different types of supernovae. Even spectra for which we do not have epoch determination, many different things. And once your dimensionality reduction is done, now you have a very stable low dimensional parameter space, and then you can work only with the ones that you are interested in. So this is type 1a supernova spectra at maximum, which is only the one that we're interested in here. So in this case, what happens was we had 150 spectra of type 1a supernova at maximum, only 150. And a wavelength range of 300 wavelength bands. So if I did any kind of analysis in this kind of matrix, the result is absolutely unstable because I have a very small number of data, and if I take out one or the other point, my results change a lot because there is not enough information to make a stable parameter space. But if I add a lot of spectra from other people, from other stars, what happens is that my parameter space becomes very stable because now my code knows how to recognize spectra in general, and it knows that type 1a supernova spectra of maximum lies in that direction. Once we did this, we did some, once we reduced the dimensionality this way, just one thing that I have to say. This obviously was not our idea. This was a suggestion from our collaborators, computer science people, and they wanted us to put inside spectra from the sun or whatever, from laboratory or anything like that. I had a huge number of astronomers in the group that kind of freaked out when we said they were going to put spectra of the sun in the middle of type 1a supernova spectra. So in the end, we ended up with only supernova spectra from different angles. And once we had this low-dimensional parameter space, what we did was we did a k-means, as I told you before, right? With four groups. So this is how you can see the full lines are the mean spectra of the groups that I found using k-means, right? And the dotted line are the mean spectra of the groups found in the literature. So the first one is it's always type 1a. So this is high velocity features. These are normal 1a's. These are 91BG like, and the last one is 91T like. So this is only for you to see that in this sense, what we wanted to do here, our initial goal, was to take this bunch of supernova spectra and data-drivenly find subtypes of type 1a supernova. This is what we wanted to do. In the end, what happened is that I didn't have a statistical significance enough to tell you there is X number of groups. So remember all of the diagnostics that I told you before about the k-means and things like that. What happens is, depending on how I make the question, I got a different answer for the number of groups. So in the end, we ended up putting number 4 because it was the number that we had in the literature, so we could compare our results with the results in the literature. But I'm pretty sure that with a better data set, more not so noisy and a larger data set, this could be done completely data-driven. So now a little definition, a very quick definition, so we can just mention a little bit of deep learning. What is neuron, right? We're going to start. This is the basic elements of a neural network. A neuron is something that takes an input, do some linear transformation like this, and gives you an output, right? This is a neuron. If you want to do a neural network, what you do is you will have a network of nodes here, and what would happen is so suppose, for simplicity, that I'm doing photometric redshift, right? So if I'm doing photometric redshift, each one of those axes would be magnitudes in different bands, for example. You see that each magnitude goes to all of the nodes. So each node receives all of the input variables and outputs one number. In this case would be the photometric redshift, for example. And you remember that from this you have these W here are parameters that you need to fit. W and B are parameters that you need to fit. So here you will have a set of weights that you need to do. When you're training your network, what you do is you input the features here, in this case the magnitudes, and you know what the redshift is because you have a training sample, and then you find the weights corresponding to these nodes that will better reproduce your data. And this has been done for a long time in astronomy. This is from 2003, but I'm pretty sure that, at least for photometric redshift, this thing has been done since the 90s or something. So it has been done for a long time in astronomy, and it is pretty well established that it can have significant comparable results with other methods. And when you are going to go deep, the difference is now that you have more than one layer here, you have different deeper layers. Depending on where you see the definition, they have a threshold for what you consider deep. So many people will tell you that 2 layers is not actually deep, it's a shallow network. But the point is that when you have different, the point is that between the input layer and the output layer, you can have many layers of this. And this configuration can be different. You can have different numbers of neurons in each one of these layers. And there is no hard code recipe of how to choose those layers. When you train your network, you have your input, because remember, this is supervised learning. You have your input, you have your output, because in the training sample you know the labels, and you are trying to find the weights of these neurons. Once the network, and this is the computationally expensive part. Once the network is trained, you can input some other thing that you do not have the label from, and the network will give you the estimated value of the label. And this can be as complicated as you want. So remember that I told you that each neuron had a linear expression within that. But you can also have, you can add non-linearities, and at each neuron you have an activation function that you cannot see, but can be a tangent or a sigma. Anyway, you have many different options that you can have for your activation function, and this has been extensively explored in astronomy. So I got only a few examples of galaxy morphology, of a study of radio sources with Galaxy Zoo data. I think everyone is familiar with Galaxy Zoo. Yes, no, yes. And deep learning for 21 centimeter images, and these are only very recent examples that I got you. So this has been extensively applied to astronomy in many different scenarios, and it seems to work quite well depending on the area and on the metrics that you use. So, as I said, this was the first part. What I would like you to, everything that I told you right now, there was static data. In the sense that you can do unsupervised learning, you can do supervised learning, you can do transfer learning, you can do semi-supervised learning. Everything that I told you about, the data is static, okay? You begin with and that's the data and you have to deal with it. I just wanted to remember that anything that you can do with this is only the tip of the iceberg. You have a whole bunch of things here where your code can adapt, and you can put the human in the loop in order so you can have a better estimation of your classifier of your regression system. So one thing, what I wanted to remember is that everything that we talk about now, it's called passive learning. And now we are going to go to things where things get a little bit more interesting. So adversarial learning is what happens when you have a worthy opponent, right? So in adversarial learning, what you're going to do is like this. You have, for example, suppose that your problem is you have an image or you have a message from someone and you want to understand if that's a real image, if that's a real message, or if it's a fake, right? If it's a bogus or something. So you have your real world samples here, right? And here you have a generator, you have a code, a network or a simulator that simulates a fake sample, right? So, and here you have a discriminator. So in this case, you have two neural networks working together. One that can to generate your sample, and one which is the discriminator, like that. When you're going to train, what you're going to do is you're going to feed this discriminator with a real-world image and with a bogus image. And then you say if this is real or not, and you're going to minimize this loss function. And you're going to do this many times. As these systems develops, what happens is that this guy gets really, really good in producing fake images, because he will understand how to generate images which are closest as possible. And the challenge here is that this guy becomes as well a very, very good discriminator of what is bogus and what is not. In the end, once you are happy with your training, once things converge, you can either throw all of these things out and then you have a very good discriminator for bogus and real images, or you can throw all this part out and use this guy as a simulator of your data in order to have very nice simulated images. This has already been used in astronomy. In order to, this was an example that they did with images of galaxies. So what they did was they had the original image. They degraded the image, so they make the image worse on purpose, and put it through the generator, and this is what you get in the end. So their goal here was actually they were interested in this part. So they were interested in producing something that would produce high resolution or high quality images. So you see that here you have the original image. Here is the degraded image that was fed to the network, and this is the generated image. You cannot see very well, but the slides are online, so you can see that sometimes you can even get hyper-resolution images, which means that in the end you will have a higher resolution here than you would have in the original image. This for now is only an exercise of how these things can be done, but this is I think this is very interesting.
Excuse me, can you explain how it works in the slide before?
This one.
How you train the better resolution?
This one.
No, the next one.
This one.
Yeah.
Yeah. So what they did, here was they had the original image. Their original image was degraded, which means it was make a low resolution image, and this was fed into what they call the simulator, right? Which is this part of the network. So this simulator, when inputted with this image, would generate a recovered image. And all of these guys, both the original image and the recovered image was put into the simulator, of the discriminator. This was done because actually what you want, this guy has to be very good in discriminating between them. So the differences between these two is tiny. So if you are able to define a discriminator which can actually recognize those images is one of the things that you might want to do. It's okay? And the other thing that I also could not find any applications to astronomy, but I think it's quite good, it's reinforcement learning. So reinforcement learning is how we learn. So it's importance of positive feedback of what you're doing. Everything that I could find in reinforcement learning was extremely theoretical at this point, but one thing that the most applicable thing that I could do was how you teach a robot to walk, right? That was the most applicable thing that I could find. So, for example, if your state is your left foot is up, and you move your foot forward, you get a positive point. If your foot is up and you put your foot down, you don't get anything because you didn't move. If your left foot is up and you move your foot forward, you get a lower number of points. So this means that the network will try many different actions, and depending on the outcome, that someone will give a feedback if that was a good or a bad thing, and that will help you improve your results. This is very nice, and I would like very much to see some astronomical application of this. The main thing that I would like to talk to you about today, which is because I think that is actually something that is absurdly important for astronomy, is active learning, or how you can get the maximum, the most of your classifier of your regression system with the minimum possible number of training. Okay, and the idea here is that you will have an initial training sample. You learn your model, so you train your model learns something. So here you have this boundary between these two things. And then the algorithm goes to the unlabeled pool and will check which one of your points that you do not have the label would be most beneficial to your classifier if you have the label of that point, right? So it would identify which one of your unlabeled data is most important to improve the efficiency of your classifier. And then it will make a query, and this is where the human gets into the way. So this can be a human, or in our case, a telescope or whatever, someone who can give an answer. And it will make very few, but very important queries, and this will be put back into the label pool, and this thing will be done again. So at each iteration, you improve the classification results. You improve your classifier. So the question that you want to answer is, can machines learn better with fewer labels if they are carefully chosen? And the answer is yes, and this has been used in many different scenarios. So one scenario as this is used is span classification. So when you get your new mailbox is what is a span from a random person. with times, once in a while, you will recognize that the algorithm on purpose put in your mailbox an email that is obviously a spam for you. But if you actively classify that as a spam, you help train the algorithm to personalize the spam classification for you, because what is a spam for you might not be a spam for you, things like that. The other things, which I'm not sure if it works very well, but it's recommendation systems. So it says that 35% of the Amazon sales is based on the recommendation system made by the website, and 75% of everything we watch on Netflix is a result of what they offer us to do. Everyone who has a Netflix account knows that this did not work so well if you randomly click in some film you are not actually interested in. It keeps offering you that kind of movie forever. So it obviously needs improvement, but anyway, this is how it's done.
Can you use active learning for regression problems?
Yes, yes, as well, you can. It's the same, it's basically the same thing. And another place where this is also used is drug testing. Because if you are developing a new drug, you want the highest possible accuracy in your result, but for obvious reason you have to test in the minimum possible number of people, right? So this is something that is also, this kind of algorithm is also used in order for you to decide if you have enough drug testing or not, or something like that. And the other application is speech language processing, speech to text in engines, or translation for not so common languages and things like that. So where you have can have an annotator. Every person is able to. Almost everyone is able to listen to a text and put that in, listen to someone speaking and put that into a text, but you have a very few number of annotators and you have to do that with parsimony. This has already been done in astronomy for a long time, actually. There was this paper on the estimation of stellar parameters from 2005, which was completely ignored by the community. I'm not sure exactly why. I think first, this is not a very famous group. This is a Mexican group which nobody actually knew. The second thing is they do not have very fancy plots, and we know that for astronomers that's very important. They only have very simple histogram, and I think that's one thing that got into the way. But it was the first thing that I could find of active learning in astronomy. Another possibility is classification of variable stars. So if you see, in order to classify a variable star, you need a spectra, and spectra are very expensive, and we know we can never have as much spectra as we need to classify all the photometry that we have. And so this result shows that this is the error rate. These are different classifiers, and these are the results for the same classifiers, but when you do the active learning update. So you see that the error rate is actually lower. And another application of this was a very nice one, which was they were deciding where to point the telescope in order to optimize the classification of this very different number of objects. So this is cumulative. This is the observing time. So you see that the accuracy goes up as you optimize this. And this will be extremely, extremely important when we go to the next generation of telescopes. So,
try to enter blue.
No, that was not what I was expecting. But anyway, what I'm going to say, what that slide said is, as I told you before, I work in type 1a supernova cosmology and machine learning applications. You cannot see, but here you should see the LSST, the sky over Chile, where LSST is going to be, and the video should show you animations of supernova happening in the sky. But my point is, we know that supernova 1A are famous for cosmology, and everyone promised they would have many type 1A supernova for cosmology, and we have to fulfill that promise somehow. The first results of 1998 had 42 supernova in the results. The GLN sample has now 740. We can think that we have like 1,000 for around type 1 supernovae. And by 2015 to 2025, we expect to have more than 10,000 type 1a supernovae. This means that LSST will have 2 million alerts a day, 2 million alerts a night, or 15 terabytes a day. And 40 nights of LSST is equivalent to the entire Google database, and LSST will run for 10 years, right? We will never have spectra for all these guys. So if we want to have a reasonable classifier, if you ever want to use this photometry for something, in this case for supernova cosmology, we need to decide how we are going to do spectroscopic follow-up. So the problem is like this. You'll have a very small sample for which you'll have photometry and spectra. Remember, this sample is extremely biased because you have all the observational bias that comes with spectroscopic sample. And you have a huge photometric sample that you need to have some classification for. And all this bias that I said, they come in different flavors. So you see here I have the training sample in red and the target sample in blue. So you see that you have whole regions of the parameter space. These are magnitudes in G, I, and Z. You see that you have entire regions of the parameter space where you do not have one example to learn from. And on the other hand, type 1a supernovae are very famous and everybody loves them a lot. So which means that our training sample, which is our spectroscopic sample, has a huge number of 1As in comparison to what we expect to find in the target sample. So this is absolutely non-representative. And if you remember what I said yesterday, you should not expect any machine learning model to work if you do not have a representative sample between training and target samples. So the question is, how do you construct training samples which optimize the photometric classification results given the observational constraints that we have to deal with them? And then here has points to take into account. Remember that a spectroscopic sample was not constructed to be a training sample, right? What you do in astronomy is we take the sample for which we have spectra because we have labels for that guy. We train our machine learning models on that, and then we apply in the photometric samples for which we do not have spectra. The spectroscopic sample was never thought to be a machine learning training sample, right? The guy who built that was thinking on other things. Also, you have to remember that the training data dictates the limits of your photometric classification. So you will never be better than what your data is telling you. And a spectroscopic follow-up should be used with parsimony. So this is the strategy that adapted to the active learning part that I told you before. I have the raw data, so I have my light curves in many different filters. I do a parametric fit. So I have a parametric function that tells me how I can fit to the supernovae. So for each filter, I will have 5 parameters. I concatenate these 5 parameters for each one of my filters in the lines of my matrix, and in this way I have a complete, beautiful matrix. I do a random forest for this. Remember that random forest allows me to have a probability for each one of my classifications because I have many votes for each one of the trees of the random forest. So I choose the guy with highest uncertainty in the classification. And I put this guy I make a query. So I say, okay, I want to know the object, the class of this guy. This guy is put in the training data again, and I do this many times. Okay? Yeah.
Can I ask a question, maybe very special? The random forest is the ensemble of strong classifiers, or regressors in this case. And these actually regressors are over-trained.
They are overtrained.
Overtrained. Every regressor in random forest actually is overtrained because, and the average gives you better. It's overtrained because you need to lower the bias and you don't think about variance. And after you make average, you lower the variance in random forest. The problem in the probability function from random forest is that it is not. Do you check that this probability function is a real probability function? Because it can be over too broad, for example, or do you calibrate this probability?
No, I didn't calibrate anything. This is, I agree. I understand what you're saying. In this case, all of these steps of this pipeline is the most simple possible thing you can do. There was absolutely no check at all, right? I'm just one because this is I forgot to say, this is simulated data from the Supernova Classification Challenge of 2010. So I know the ground truth because this is a simulation, okay? And actually at this point I need to do this as a simulation because I need to know if I'm right or not. But that's the only point. But from whatever I'm going to say from up here, just remember that every one of these things can be done in a better way in some situation. But the results is something like that. So figure of merit is what you have to optimize when you are doing supernova photometric classification. This is the number of queries, so the number of things you added to your training sample. You see that the canonical strategy basically doesn't do anything because you are adding data, but you are adding data from the same underlying distribution, so we actually don't add information. The yellow line is what happens when you take random samples from the photometric sample, right? Because you have to, even if you take random samples from the photometric sample, it's already better than what we're doing right now because you have a very, very biased sample. So this is what happens when you random sample from the target. From the observational point of view, this yellow line is not very realistic because you would have telescope times and stuff, but we will talk about that. And the blue one is what will happen when you do the very simple active learning that I talked to you about. So this was also a result of interdisciplinary collaboration that I work on. And what happened in order to get to this result was I took the supernova data, I pre-processed, gave them a very beautiful matrix for training and for target, and I said, learn something. And I give to the computer science guys. And then they come back and said, it's impossible. Because your training is so different from your target that you're never going to learn anything, right? And then they suggested this. And then I said, this is useless. Because I cannot go back and ask for a spectra of a supernova that's not there anymore, right? The supernova fade away. So if you keep talking with those guys, you can like get around these things. And this is what we did. So what we did was we decided to incorporate the time domain aspect of a supernova survey in this question. So bear with me here, okay? Everything, that whole circle that I said, is going to be done every day, right? So I'm in the first day of my survey. For each day of my survey, I count every supernova for each I have at least 5 points in each filter. Right? If I have at least 5 points in each filter, this is considered an observed, an available supernova. If today that supernova has a magnitude lower than 24 in our band, I will put that supernova in the queryable sample, if that's a word, like the sample available for querying. Right? If it's not bright enough, then it will go to the target sample, and I do this every single day. Which means that at every single day, my algorithm will only be allowed to ask for spectra of things that are in the yellow sample, because they are bright enough, and I'm considering that I have a 10-meter telescope that I can take a spectra. When I do that, and when you do these things, another thing that you can ask is, do I need an initial training at all? Because the algorithm itself is asking me the data to build the training sample, right? So you don't even need an initial training. In the beginning, what happens, you cannot see here, but you have a very up and down posterior. So these are different metrics that is used. You want everyone here to be 1, right? So everyone here, you want to be 1. If you could see here, is that in the beginning, you have some ups and downs. That doesn't mean anything because, for example, sometimes you have 100% purity in your classified sample just because you only have one supernova, one type of supernova in your sample because you're still building your sample as the survey goes by. But if you take it for 180 days, so you see this arrow here shows my result that I got with a static sample, with the training sample that they gave me. I just trained in the training sample and estimated in the target, and I got the result of this arrow. And this training has 1,100 spectra. Here I got almost to the same result of active learning with only 180 supernovae. So you can see that you can highly improve your classification, even if you have a lower number of spectroscopic resources, just because you are choosing correctly whatever you have to do. And then if you go to the queryable or queried sample, so after everything is done, now I go back and I'm going to check what are the objects that the algorithm asked for, right? So you see here in the red, you have the distribution of the spectroscopic sample. In blue, you have the distribution of the photometric sample. And in black, you have the distribution of the objects that the algorithm queried for. So you see, they are not it's not very different from what you would normally do in your spectroscopic sample. And it couldn't be, because I made a magnitude limit. I put a magnitude limit on it, right? But I have a few guys at very high redshift, and it also tells me that I do not need many of these objects that I have before. It shifted the way I divided my spectroscopic time, but in the end, it was I ended up using almost all. Okay, so this for some reason is here, but I ended up using the same amount of spectroscopic time that I was using before with a small number of samples. So what I wanted you to remember from this is the question is, how do we optimize machine learning results with a minimum number of labeled instances? And this is very important in astronomy because of the spectra photometric stuff. I'm not saying that this specific algorithm is the answer. I think, first, I do not think this data is a very good data to get a clear result about this. This is a no data. But my point is that if we want to improve our machine learning results, we need to go to some adaptive learning technique, which means that we are probably not the best people to choose what goes in the training sample. Right? If you let the algorithm itself ask you, let you know which samples do you need the label for, you're probably going to get a better result. And again, this all should be, it's very important to have domain people working on it, because we have, in astronomical data, we have a lot of caveats, and it's very important that we do not take these algorithms for granted and apply it in our data, but we have to adapt them to whatever we need to do in astronomical research. I think it's better to close this. Otherwise, it will wet your computer. Okay, so I have some final thoughts, but I still have 12 minutes. So, do I have questions on this? Comments? Complaints?
I have a question, maybe outside the scope. This work is for LSST project. Is it open for the people outside? I mean, these activities about machine learning and deep learning or something like this to improve algorithms. Is it open for people outside the LSST team?
Yes, yes, I will talk about this in my thoughts. But just a remark. These results that I did, that I showed to you, was done with simulated data from the ES from 2010. So this is old. We are working now in a new sample for LSST, and this will be completely public. So I'm going to talk about a little bit more about this. Other questions, complaints? No? Okay, don't be shy. So I want to take my last 10 minutes just to give you some final thoughts of how all of this meant to us, right? I think that we will also have to adapt. Machines are not the only thing that are in their final stage. As I told you yesterday, the adaptive learning is the 4th generation of machine learning algorithms, but I do not think, it's obvious that we will also have to change the way we work and the way we interact with our data and the way we do our science. And we are getting there. I'm positive. I have a positive view on this. I think it's important in the end of a machine learning talk, we talk about developments in human learning, because that's what we want to optimize in the end, right? One thing that was very important was the open source, the open source philosophy that appeared with the computer and the internet and everything. So now you have your code, you can put your code open source, everyone can go there and look at it. And this is a positive change of mind from a proprietary thought that we had before. Another thing that is very nice is not only that we have open source code, we have community code development, which means that you have this whole bunch of people working from many different places, people who have never seen each other, and for some reason they think it's okay to collaborate in some random project that will going to benefit many different types of people. This is very nice. Obviously, we have to think if this model is sustainable in the long run. I don't think it's bad that we still do not have a result, our answer for this, but we do need to think about it. This is a slide from Kelly Cruz from Python and Astronomy this year. So you see, if you put together matplotlib, NumPy, and pandas, you come down to 15 maintainers, which means that all the Python science we do relies on 15 people not getting hit by a bus, right? So this, obviously you have a lot of people who contribute to the code, a lot of people who work together, but the point is that these are a really half burden for a very few number of people, and this should be, and we should think about how we want this system to function in the long run. As I said, I don't think it's bad that we didn't figure that out yet, but I think that's something we should think about. And then also developers in human learning is data challenges. So not only the industry, but in science as well, we learned that although, yes, we have our very complicated problems, if you phrase that in a way that normal people can understand and contribute, you can actually find ideas that you haven't thought before. I do not think that challenges are the answer, that you are going to make your science problem into a data challenge and someone will find a solution that you have never thought before for all your answers, but you will have here and there small ideas that you can adapt to your science, and that's very profitable. And the most well-known platform for this is Kaggle, right? Which is a platform for open data challenges. So you can go there. There's a bunch of data sets, and they have prizes and things like that. Another option, which has also a collaborative phase, is RAMP, which is developed by the Paris Center for Data Science. And the difference of RAMP is that it includes a collaborative phase on it beyond the normal data challenge. So here is time, okay, and here is the score. So you want this to be 1. This graph shows how the score of the people participating in the data challenge evolves with time. So you open the challenge, so you have a single day here. So this is what you would normally get with a well-trained neural network or something like that. So this is the first stages. Then you give people a little bit more time, and you see that the few people who keep working on the challenge goes from here to here. So this is the diversity gap for different people thinks about the problem in different ways, and then they come up to different solutions, and they can come up to here. And then what happens is that if you want to give a prize, you will give a prize in this stage, right? If you want to award the people who are doing this, you are going to do this in this stage. And after that, everyone can see each other's code. And this is the human learning part. You open the code for everybody to see each other's code, and they collaborate in developing a new algorithm using all of the ideas that random people have done. And then you see the human gap. So from here to here is how you can improve the result of your method if you let people collaborate between themselves. And I think that's a very good idea. And for the question that was learned, in LSST, there is a pretty, not only in LSST, but in the whole community working on photometric classification for transients, not only for supernovae. The one that I told you about was only for supernovae, but this is a problem for everybody who works on transients, is that the whole community who is doing this has been doing this for a while, and we need fresh new ideas. So we are putting together LSST, plastic stands for Photometric LSST Astronomical Time Series Classification Challenge, and I did not make the acronym, so that's not my fault. But the point is that we are putting together a new data set with simulations from LSST, and this will be an open challenge, so everyone can participate, and we do not want only astronomers to participate. We want to actually have a broader community working on this. This would be simulated, as I said, simulated light curves, so there's no images in this challenge, it's only light curves. It will be equivalent to 3 years of LSST data, which is around 15 gigabytes of data, and you will have 3.5 million objects to classify, million light curves, in each one of them in 6 different filters for LSST. The old data that I showed you before was only different types of supernovae. This time we would have different types of transients, galactic, extragalactic, periodic variables, anything. And I cannot tell you it much more because there's a huge secrecy policy about what's going on in the challenge, so I cannot tell you much about the models. But I can tell you that there is going to be a small training sample, and there is going to be non-representativeness in all of the aspects that I told you before, including there's going to be things in the target sample that are not in the training sample, so we want to see if people can find that. This is not going to be one challenge, this will be a sequence of challenges. So the first one will be released in Kaggle, and this would be a simple full light curve supervised learning exercise. You have a training, you classify the targets, that's it. And this should be done by summer. So our expectation is that by the end of summer, the challenge will be public, and you will have like 3 months in order to develop the algorithms and get around. And after this, there's going to be a second phase with more complicated questions, because we also want to understand, have light curve classification, novelty detection that Kaggle doesn't allow you to make those questions. So those are probably gonna happen using RAMP. If you are interested in this, if you want to get ready and get to know the data, there is this plastic starting kit that I developed with Alex from CDS. So this is a notebook that allows you to play with the old challenge data. So this is not the data of this new challenge, but the format will be more or less the same. So this is so you can understand how the data will come, how the light curves look like. It's not, it's an old data, but if you want to try that, this is a good way to try to get used to the data before the new data arrives. And if you know me, you know that I have to talk about this. And another thing that I want to say is that all of this are developments, as I said, in human learning. And I really, really believe that we should think about how we incorporate all of these new changes, because you see, almost everything that I talked about didn't happen within academia. This happened in the outside world. And we have to understand, we have to think about what we want our academic system to be in a world where we have to compete with industries for smart people, for young people, with things that are developing so fast that we cannot keep up with, how to develop interdisciplinary collaborations, and how to make these things blend together friendly for the human aspect of the thing as well. So if you want to have a talk about that, I'm very interested. So this is the interdisciplinary group that I mentioned a few times. If you go to this website, you can see all the kinds of projects that we do and what we work on. This is just a first try, but I really think that we should also be thinking about what we want for our academic system in the future, because it will change at some point. It's important that we are active on those changes. So my time is up. So a summary is what I want you to remember for this is just that there is much more than supervised and unsupervised learning. There's a whole bunch of things out there. Not only machines, but humans will also require to adapt, and we have to also think about that. And astronomical data can lead to very important developments in computer science, and this is something that I'm trying to push for a long time. Astronomical data has peculiarities that other data don't have. We have error bars, we have foreground, we have background, we have redshift distortions, we have many, many different things that not necessarily the big data community used to. And I think that if we talk to them in a friendly way, we can use astronomical data as a resource for the development of new algorithms as well. And as a last remark, just think about if we should update our academic system or not, as much as we love them. Okay, thank you. More questions? Thank you.
Maybe I can have a question about the active learning. Maybe not about, you told that it's true that machine learning techniques doesn't extrapolate. It comes from the fact that it's very complicated methods, and you also extrapolate simpler models. Very good. And actually, the question is, did you try to use unsupervised learning to extrapolate supervised learning methods? Because you have a bunch of data about, for example, photometric redshift. You have a lot of data about the photometry in catalogs, and you have very small sample of spectroscopic redshift. Did you try to use this photometric database in an unsupervised way in order to try to extrapolate the supervised models that you can run on a spectroscopic sample?
Yeah, so what is done is actually what you can do is to combine things and do, for example, an unsupervised phase prior to the supervised phase. So for example, before doing anything, you do an unsupervised clustering, right? So then you have groups, and you say, okay, I don't know what these guys are, but I know they're similar to each other, right? And then you open the labels, and if you have like one object with a label within that group, and you try to classify only that group, that allows you to do a better classification if you first do this kind of clustering in your data. The point is that with a static sample as we have, you will have a lot of groups for which we do not have any labels. And this is intrinsic. There are two factors here. One is intrinsic of astronomical data. You will never have spectral things that are very, very far away with the same telescope. So you have some observational limit on that. And on the other hand, you have the social aspect of the things, because a person sitting on the telescope will always think that it's better to have two spectra than one, because you are optimizing your spectroscopic time on that. So what we have done, we have done trying to apply the active learning in the photometric redshift case with the first stage of unsupervised learning, as I told you before, but that not actually save the problem if you cannot change your training data. You do have to be active in the choice of your training data, but that's one of the possibilities. If you do regression, the things that becomes more difficult is that when you have a classification it's a simulation, for example, so you know the ground truth. It's very easy to tell when you're wrong, right? It's because it's a classification, it's A or B, and it's a simulation, you know the correct class, so you can tell if you were right or wrong. When you have a regression, what is right or wrong becomes a little bit more tricky, because how far away you consider wrong is up to you to define. And this will influence your algorithms as well. I don't have an answer for that, but I can tell you that the regression case is significantly more complicated than the classification case. Other questions? Yes?
Can you consider the problem of extrapolation with machine learning as a knowledge transfer problem?
So depends. Depends. If you are in a supervised learning scenario, you learn by example. So you can have a parametric model, for example. If you normally, if you have a straight line that you are going through your data, even if you have data only on this, then you can actually extrapolate the line because you have a formula for that. I do not see how you could transfer the learning from places where you do not have any labels. So if you have, my answer would be, if I have at least one label of something similar, because for example, I don't need to have one object at exact that redshift that I want to estimate, but I need to have an object in a lower redshift that is close enough to that one, so my network can understand that the only difference is that it's time dilated, for example. If you have that good a data set, then you can train your model to learn those kind of things. It doesn't mean that it can guarantee to learn, but you have a higher chance of learning that. But I wouldn't know how to put that in a more general scenario where you can actually do the transfer. Okay.
May I ask another question? What do you think? So it's now very more about PR, about deep learning networks. What they do actually is the future extraction, automatical future extraction. This is a very important thing. Mm-hmm. But when the people try to use neural models mm-hmm. for example, photometric redshift, mm-hmm. They obtain the same actually results as random forest do.
Mm-hmm. Yeah.
So, what do you think? Do have deep learning models any advantages to other methods like boosting or random forest actually in reality? You know?
So I will give a very personal answer to your question. And this is not at all generalized, it's just my opinion. Okay. For the specific case of photometric redshift, I think using deep learning is a little bit too much, because you have 5 columns, maybe 6. There is only some kind of magic you can do, no matter how complex your system is, and that's why a random forest, a boosted decision tree does the job as well as anything else. If you have what I think deep learning, and we know that deep learning is very good to do, is if you have a complex system. So if your information you are putting in, if you have a lot of information that you can put in, and this information is complex, different levels of the network can learn different abstractions of your data. So each layer in the network will learn a different abstraction of your data, and then this can help you understand what's going on.
And do we have in astronomy such examples of very complex data? In astronomy, the data is very simple actually. We have a very distant object and only a flux from it.
Yeah, I think the most thing that we can, the closest that we can get for very complex input is images from nearby galaxies, because the images it's a very complicated task to ask a computer if that's a spiral or elliptical. If you look at that, you can have a pretty good idea, but to make a code that understands if there is a elliptical, but actually it's a little bit face edge on, or if it's a spiral. So I think the closest we can get is images of nearby galaxies.
Actually, it's also some kind of trick. I mean, these images is much more simpler than images in ImageNet, for example.
Yes, yes,
and
yes.
Also, you showed the the article about the morphological classification. In Kaggle, it was a challenge in the Kaggle, and they won the very simple model, not deep model, and maybe you don't need very deep models to understand astronomical images.
No. As I said to you yesterday, astronomical data, or in many, not only astronomical data. So I have been working on the next challenge. So I have been talking with a lot of people who do Kaggle challenges. And they tell me that the people who actually win the challenge, they spend 90% of the time pre-processing the data. So it's actually a word of understanding what your data is and actually having trusted labels that you can learn from. And for example, in the case of the Kaggle, if you're going to do a lot of people use Galaxy Zoo data as training, right? Because you use the classifications of Galaxy Zoo as a training for your model, for example. Then you have to put into account that humans have problems. So not necessarily the classifications that you get from Galaxy Zoo are 100% correct. Galaxy Zoo including gives you estimation of how confident they are in that classification, and you have to take that into account. One very very quick, a very funny example, maybe you know about Galaxy Zoo. So at the beginning of Galaxy Zoo, there was someone who was trying to check if spiral galaxies had a preferential direction, if you had more clockwise galaxies than counterclockwise galaxies. And obviously we know that you should not have. So they make this question for the people answering the Galaxy Zoo. And they come back with 80% of the galaxies was right-handed. And obviously someone said that there's something wrong in there. So what they did was they mirrored the images and they asked again. And the result was that 60 or 70% were still right-handed. It was not because the galaxies are more right-handed, it's because more people are right-handed. And when they do things very quickly, they have a prior in their mind that propagates into the classification they do. So you see, even though astronomical data is much simpler, we have a lot of complications that not necessarily exist in normal big data sets that you have. So answering to your question simply, I would say the point is pre-processing.
So if there are no any other questions, so thank you, Emily, for this interesting and very important.
They have a question about They have a question about how you link.
Have a question.